So in this video, I'm going to show you how to cyclize a straight chain sugar into a ring structure, and the ring structure will be a Furanose ring or a 5-membered ring. As our starting straight chain molecule, we'll use a ketose sugar as shown here on the left. So go ahead and pause the video, go ahead and try to cyclize it, and then when you get stuck or you want to see what the answer is, come on back, and then you can kind of self-evaluate as to where you may have gone wrong in the cyclization, if anywhere at all. So the first thing I would do is go ahead and number the carbons in the chain, or in the molecule. And remember, when numbering carbons in a chain like this, we want to make sure that the, in this case, the anomeric carbon, or the carbonyl carbon, should get the lowest number possible. That's something we learned about in organic chemistry. So we can go ahead and number these. The anomeric carbon, or the carbonyl carbon, is the second one from the top. And so we'll number our chain starting at the top and going down. So this will be carbon 1, carbon 2, carbon 3, 4, 5, and 6. That'll help us keep track of our carbons as we go ahead and cyclize this molecule. Now, when cyclization occurs, it's the carbonyl carbon that reacts with a hydroxyl group. We have several hydroxyl groups to choose from here. And so we got to pick the one that's going to form us that Furanose ring that we're after. And it turns out that the one on carbon 5 is the hydroxyl group that will react with the carbonyl carbon to form a Furanose ring. So let's do that. What happens in this reaction, I'm not going to go through the reaction steps and all the arrow pushing, but essentially what's going to happen here is this hydrogen will be at some point let go, and will form a new bond from this oxygen shown in red to the carbonyl carbon right there. And then, because at this point the carbon, has too many bonds to it, it doesn't like that, the oxygen that's attached to it loses one of those bonds and goes to a single bond, and then eventually a hydrogen will attach to that oxygen to form that structure. So now we sort of have the basic framework of our ring structure. I'm going to highlight here in sort of a light yellow color, if I can get it right. I'm going to try to highlight here the ring structure itself. So what's forming the ring, or what atoms are part of the ring. Notice it's carbon 2, 3, 4, 5, and then that oxygen all the way back around to carbon 2 again. Notice carbons 1 and 6 are hanging off the ring, and so are these couple of hydroxyl groups on carbons 3 and 4, and a lot of those hydrogens and hydroxyl groups on carbons 2, 3, and 4, and 5. So you can see what's kind of hanging off the structure there. So that's our ring structure right there. I'm going to remove that ring structure, or that marking, and get back to this. And so let's go ahead and just draw the skeleton of the framework of the Furanose ring. So we'll do that here. I'm going to put the oxygen right on top. That's typically where you'll see it on the internet and in textbooks. But you could put it anywhere. It doesn't really matter where you put it. But notice here now I have five-membered ring there. So that's a Furanose ring. It's 4 carbons and 1 oxygen. That's 5 total atoms. And that's a 5-membered ring. That's a Furanose ring. I also know which carbons are part of that ring structure. It's carbons 2, 3, 4, and 5, as we just recently looked at. And so therefore I'm going to go ahead and number the carbons in the ring. Now I can't just haphazardly number them. I have to number them in order. So I'm going to call this one over here carbon 2, the one down here carbon 3, there's carbon 4, and there's carbon 5 right there. So there are the 5 members of the ring. And then of course, because this is a sugar and those carbons have 4 bonds to them, I currently only see 2 bonds to each of those carbons. So let's add in the lines, the bonds, we haven't put the atoms on yet, for the 4 carbons, because we have a couple more things to annotate here on our Furanose ring. So let's look at carbon 2. And I'll kind of go slowly through carbon 2, highlighting things along the way, and then hopefully at some point we see how these will all come together. So carbon 2, notice, is bonded to 4 things. So looking back at the straight chain structure here, it's bonded to 4 things. It's bonded to carbon 3. So I'll put that a nice dark blue line there between carbon 2 and 3 to highlight the one I'm showing you. And notice here on our cyclical structure, that's this bond right there. Right, that's our connection. So we didn't lose that connection. It wasn't involved in the reaction, so it's still there. I have one bond to the oxygen. Now in the straight chain, that bond looks long and ridiculous. Obviously, that's not how it is in the ring structure. But that oxygen that it's bound to is the one in the ring, right? And so that's this bond right here. So that's 2 of my bonds to that carbon number 2. So I have 2 more bonds. I have one to the CH2OH. And so let's go ahead and annotate that. There's CH2OH. And I have one bond to an OH that's missing. So that would be right down here. Now you might be wondering, why did I put the CH2OH at the top and the OH at the bottom? Well, it can actually go either way. You could have done that either way. You could have put the OH at the top and the CH2OH at the bottom. It just depends on how that ring structure was formed. So if it was formed, let's say, think about if you had a straight chain sitting in front of you and you could actually touch that straight chain molecule. It was let's say it was a 3D structure. You could actually have taken that oxygen on carbon number 5 and pulled it toward you out of the screen and then around to carbon number 2. You could have also taken that oxygen and gone away from you behind the screen and come from the back side. So when these ring structures form, they can go either way. If it goes one way, it causes a CH2OH in our ring structure to be up on the top side and the OH on the bottom. If you go the other way, the OH would be on the top side and the CH2 would be on the bottom side. It turns out, in fact, both of those are made when these ring structures are formed, right? These are the different anomeric structures of rings. And so because of that, this ring can take on an alpha configuration or a beta. So it has alpha or beta possibilities. We'll get back to that in just a moment. But for now, it doesn't matter which way you would have put those 2. You could have put it either way. In fact, both exist when the ring structure is formed. Let's go on to carbon number 3 now. Carbon number 3, we have the OH on the right and the H on the left. Remember, there is a nice mnemonic device that can help us with this, and that's LERD. L stands for left, U is up, R stands for right, and D is down. So if the OH group, so looking at carbon 3 in the straight chain structure, if the OH group, well, the OH group is on the right, the H is on the left. So the atom on the left goes up because L in LERD, LU is left up. So H goes up, so I look at carbon number 3 here in my ring structure, and I put the H in the up spot. Because the OH is on the right, it's on the downside. So I put the OH on the downside. And that does matter. You can't, if you flip that, you've actually made a completely different sugar. So you do not want to switch those. Those have to be where they are in these structures. In carbon number 4, the hydrogen's on the left again. So the hydrogen goes up, and the OH is on the right, so it goes down. Now we move to carbon number 5. Because number 5 was involved in this new bond, we don't worry about that whole LERD thing because it was involved in the bond. Let's go look at where those bonds are currently. So notice, looking at carbon 5 in the straight chain structure, we have a bond between the carbon 5 and carbon 4. So that's right here. We have a bond between carbon 5 and the oxygen in the ring. So that's right here. And then once again, we have 2 different groups of molecules or hydrogen atom on this structure here. And so in this case, we typically will put, if it's the D conformation, I'm not going to get into this too much, but notice on carbon number 5, there is a bond between carbon 5 and carbon 6. Carbon 6 is outside the ring, so I just showed that here, and I put the CH2OH up. And then the hydrogen is the other molecule, and so it will be down. And so that would be the appropriate way when drawing a D conformation of a sugar, which is what we had originally. You would always put on carbon 5, or in this case on carbon 5, you put the CH2OH. The CH2OH shown here would be up because this is a D sugar. In an L sugar, it would be the opposite. So in this case, you don't dictate which one's up or down. It's actually D versus L. That gets a little bit more involved for us, but at this point, if you're dealing with a D sugar, just draw that CH2OH on the upside on that carbon 5, and the hydrogen would go down. And so there is the ring structure of a Furanose ring. Notice it's a 5-membered ring, so it is a Furanose ring. And notice carbons 1 and carbon 6 are hanging off of the ring structure themselves. They're not part of the ring structure as part of one of the atoms in that ring structure. The next question is we'll just finish up with going back to which form are we staring at, the alpha or the beta. So to determine that, you first find the anomeric carbon. In our anomeric carbon, I will circle in red. Our anomeric carbon is right there. I know this because this is the only carbon that's directly bound has 2 bonds to oxygen. It has 1 bond to oxygen if you look straight down at that hydroxyl group, and it has another bond to the oxygen in the ring. If you look at any other carbon in this structure, there is no other carbon that is bound, has 2 bonds to oxygen. And they can be the same oxygen or different oxygens. It doesn't matter. It just has two of the 4 bonds to that carbon are to oxygen directly. So that's our anomeric carbon. So to determine whether it's alpha or beta configuration, you look at the anomeric carbon and you find the hydroxyl group attached to that anomeric carbon. And that hydroxyl group is right here. You then look at you then go from across the oxygen atom in the ring from that anomeric carbon. So in our case, we'll go from the anomeric carbon to the oxygen in the ring over to the carbon on the other side of that oxygen in the ring, which in this case is the 5 carbon, and you look for the large group. Notice the large group on the other side is up. So I have so I've circled the 2 that we're looking at, the large group on carbon 5 in this case, and the hydroxyl group on the anomeric carbon. Notice one of them is up and one of them is down. If one is up and one is down, it doesn't matter which is up and which is down, but if one is up and one is down, it is anti. And so this is a Furanose ring in the anti configuration, or in the anti configuration of the ring structure. Now just to show you just so you can see the difference, let's say originally we had put the OH up and the CH2OH down, which again would be perfectly reasonable. That happens. So let's go ahead and put the OH, got that wrong. This is going to be the CH2OH is down now, and the OH is up. And again, like I said before, both of those configurations occur when the ring structure is formed. Maybe not the same percentages, but they both form. And so now let's figure out if it's in the alpha or beta configuration. So again, we find the anomeric carbon. It is right here. Notice again that this is the only carbon that of its 4 bonds to it, 2 of them are 2 oxygens. So there's one to there, and there's one to there. So there's our 2 bonds to oxygens. So we found our anomeric carbon. Now you look at where is the hydroxyl group attached to that anomeric carbon, and you can see that it's right there, so it's up. Now we look at the carbon on the opposite side of the ring structure oxygen, or ring structure atom of oxygen. So there's our oxygen. We go to the other side. In this case, again, it's carbon 5. The large group on carbon 5 is up. The OH is up. Since both of them are up, this would be the beta configuration. If both of them were down, it would be beta. So if both are up or both are down, it's beta. If one is up and one is down, it's alpha.